Imagine this for a moment. April, May 2023. This is just unprecedented heat wave sweeping across Southeast Asia, temperatures in places like Thailand, hitting a staggering 49 degrees Celsius. Now just pause and think what that actually means for a region where, agriculture, fisheries, tourism, they aren't just industries, they're the lifeblood.
Yeah.
Crops just wither, fish die off, tourists, well, they stay home. It's a really stark, visceral picture of our changing climate. And, while we talk a lot about cutting emissions, that urgency, it's led to this growing search for complementary and often pretty controversial solutions.
Indeed. Global warming, which is just relentlessly driven by greenhouse gas emissions, it's intensifying these extreme weather events, especially heat waves, and particularly in incredibly vulnerable regions like Southeast Asia. We've seen the ambitious goals of the Paris Agreement, right? Aiming to limit temperature rise. Well, they're proving incredibly challenging to actually achieve. Mm-hmm. So yes, that search for additional tools, it's become increasingly urgent.
And that search brings us to something that honestly sounds like it's straight out of science fiction.
Yeah.
Solar Radiation Modification, or SRM. For anyone who might need a quick refresher, it basically involves actively trying to cool the planet by reflecting sunlight back into space. Can you give us the quick rundown on what SRM actually entails?
Absolutely. So simply put, SRM covers techniques aiming to reflect a portion of incoming solar radiation back out, the goal being to induce a cooling effect on Earth's climate. This recent study, which is what we're really digging into today, it looks at two main approaches. One is marine cloud brightening, MCB, that tries to make low-altitude clouds more reflective by dispersing tiny sea salt particles into them. The other, and this one gets particular attention in this research, is stratospheric aerosol injection, SAI.
Right. SAI is the one that sounds a bit more dramatic, isn't it? Deliberately injecting reflective aerosols way up into the stratosphere. What makes that approach so compelling? Why is it getting so much research focus?
It is quite dramatic, yeah. SAI involves deliberately putting reflective aerosols, like sulfur dioxide, into the stratosphere.
Yeah.
They form a layer, basically, that partially blocks incoming sunlight. What's fascinating here is that SAI has grabbed attention not just for its potential for, significant cooling effects, but also because it's seen as relatively low cost and feasible maybe for short-term deployment. And we even have this real-world sort of analog for its effects. The 1991 eruption of Mount Pinatubo, it released huge quantities of sulfate aerosols into the stratosphere, and, well, it resulted in a temporary global temperature decrease. Nature kind of gave us a preview.
That's a pretty powerful natural experiment then, a real-world demonstration. But despite these seemingly positive possibilities, SRM, it's still highly controversial. What's the biggest objection, the sort of big question mark hanging over it that critics always bring up?
Yeah, the core controversy, and rightly so, I think, lies in the significant uncertainties. We just don't know enough about its long-term ecological, climatic, and, importantly, socio-political consequences. Concerns persist about potential unintended side effects, things like disrupting regional weather patterns, shifting vital monsoon systems, or even creating, unfair impacts on already vulnerable populations. It's a powerful tool, potentially, but one that comes with a lot of known unknowns and maybe even unknown unknowns.
And to try and get a handle on these ramifications, this study uses something called the Geoengineering Model Intercomparison Project, or GeoMIP. What exactly is that framework? Why is it so crucial for scientists trying to assess the potential impacts and risks of SRM?
GeoMIP is this big global collaborative initiative. It's essentially a standardized scientific playground, if you like. It's designed to systematically evaluate how SRM might affect various parts of the Earth system. It gives a structured framework for comparing results across different climate models, which is absolutely crucial for identifying where the projections agree and where they differ. Think of it like running the same experiment in multiple independent labs and then comparing notes. It helps build confidence, but also flags where we need more research.
Okay, so let's get into the real nitty-gritty of this specific study then. Published just days ago, July 5th, 2025. Impacts of solar radiation modification on temperature extremes and heat waves in Southeast Asia. What scenarios did they actually analyze to project SRM's impacts out to, 2099?
Right, so the study put 4 key scenarios into play for that period, 2020 to 2099. 2 were they call emissions pathways.
Yeah.
SSP245 represents a sort of moderate emissions pathway, a middle ground scenario where emissions eventually stabilize. Then there's SSP585. That's the high emissions pathway, essentially a business as usual path where emissions keep climbing largely unchecked, pushing warming to really extreme levels.
Okay, so those are the futures if we basically stick to our current emissions trajectory. But what about the specific SRM interventions? How did they actually model dimming the sun?
Exactly. So the two SRM intervention scenarios are G6Solar, which models a direct reduction in incoming solar radiation, like a global dimming effect, essentially. And then G6Sulfur. This incorporates the stratospheric aerosol injection using sulfur dioxide, mimicking that Mount Pinatubo effect we talked about.
Yeah.
So these scenarios provide this really comprehensive comparison, right, to see how intentionally altering solar radiation might change the future compared to just focusing on emissions.
Now, to make sure the projections were really solid, especially for a region as complex and diverse as Southeast Asia, how did the researchers achieve accuracy? What was their methodology like?
Yeah, that's key. They took a multi-pronged approach. First, they used an ensemble mean from 4 different Earth system models. Think of it like getting a consensus forecast from 4 top climate modeling groups. And crucially, for regional accuracy, they did this vital step called downscaling and bias correction. Imagine taking a kind of blurry satellite image of a whole continent and then zooming in, sharpening it, and adjusting the colors so it perfectly matches the ground truth for individual neighborhoods. That's sort of what they did, using high-resolution ERA5 reanalysis data as a reference baseline to make sure their predictions were as precise as possible for Southeast Asia's varied landscapes and climates.
And to really measure the heat, they went beyond just asking, how hot did it get? What specific metrics were they looking at? What did each one tell us?
They focused on 6 very specific metrics. It gives a really detailed picture of both the temperature extremes and heat waves. For temperature extremes, they looked at TXX, that's the annual maximum, daily maximum temperature. Basically, what was the absolute hottest daytime temperature reached all year. And TNX, that's the annual maximum daily minimum temperature. So how sweltering did the hottest night get in a given year? Really important for health impacts.
Right, because that nighttime heat offers no relief. Okay, and for heat waves themselves.
For heat waves, they use a very specific definition, at least 3 consecutive days, where the daily maximum temperature goes above the 90th percentile of what's normal for that specific place and time of year. Then they measured everything about them. HWN, the heat wave number, so total events per year. HWF, heat wave frequency, the total number of days spent in a heat wave per year. HWD, heat wave duration, the length of the longest single heat wave event per year.
Yeah.
And finally, HWA, heat wave amplitude, basically. How much hotter than normal was the peak temperature during the worst heat waves? Yeah. This allowed them to really understand heat's full assault, not just a single number.
Okay, so armed with those metrics and those scenarios, what did the models project for Southeast Asia? Let's start with the grim outlook. What happens without intervention under that high emissions SSP585 path? Can you paint the picture for us?
Well, under that business as usual SSP585, the picture by 2100 is quite stark. Yeah. Annual maximum temperatures, that TXX metric, they're projected to soar by 4 to 6 degrees Celsius compared to the baseline period. That's a huge jump. And the heat wave characteristics, they intensify dramatically. Duration, HWD, could rise by 40 to 180 days. Occurrences, HWN, might increase 3 to 5 times. And the intensity, HWA, could escalate by 5 to 6 degrees Celsius. It's a profoundly challenging future.
Okay, and here's where it gets, I think you said, really interesting and frankly a bit terrifying. What did the study find specifically for maritime regions under that high emissions scenario towards the end of the century?
This is a truly, truly concerning projection. For maritime regions, think Indonesia, Malaysia, the Philippines under SSP585 by late century. Heat wave frequency, HWF, could reach 280 to 340 days a year.
Days a year.
Days a year. That's approaching year-round heat wave conditions.
Wow.
And heat wave duration, HWD, could increase by 140 to 180 days, meaning individual heat waves persisting for nearly half the year. It's a scenario of prolonged, intense, and, well, almost unimaginable heat. It really makes you wonder how people could even function, how ecosystems could survive.
So that's the problem laid bare, a truly terrifying prospect of almost constant, intense heat. But here's where the study introduces the potential antidote, right? The solar shield idea. How effective did SRM actually prove to be in dialing back these impacts?
Okay, so the study found that the SRM scenarios, both G6Solar and G6Sulfur, they do effectively moderate these severe impacts. They bring them much closer to what you'd expect under the moderate SSP245 scenario, the one with some climate action. For temperature extremes, under SRM, those TXX increases are generally limited to about 2.0 to 2.5 degrees Celsius. TNX increases to maybe 2.0 to 3.0 degrees by 2100. Still warming, but much less severe. And crucially, for heat wave intensity, HWA. SRM scenarios constrain those increases to 2.5 to 3.0 degrees Celsius. That effectively halves the intensity compared to the high-emissions SSP585 pathway. SRM also significantly cuts back the increases in heatwave frequency and duration. It prevents those near year-round heatwave conditions we saw under high emissions. It's a really profound reduction in immediate climate stress.
That is a significant moderation, truly. But when we talk about having the intensity heat waves, it almost sounds, well, almost too good to be true. What are the nuances here? For instance, did SRM work equally well during the day versus at night?
This is a critical finding, and it gets right to the nuance. SRM turned out to be more consistently effective at controlling nighttime temperature increases, TNX, across all the subregions they looked at, compared to daytime temperatures, TXX.
Okay, why is that?
Well, it's likely because nighttime temperatures are more directly influenced by SRM's direct reflection of energy back to space, what scientists call radiative forcing. It's like turning down the planet's heat source more directly after the sun goes down. Daytime temperatures, though, are messier. They're influenced by lots of other things, like how the land surface heats up, cloud cover, local air currents, convection. All that makes them less uniformly responsive to just reducing incoming sunlight. So the key takeaway here is that SRM isn't some uniform fix, right? Its effectiveness changes depending on the time of day and the specific local conditions it's interacting with.
And was there a difference between the two SRM approaches they modeled? G6Sulfur versus G6Solar. Did one perform better?
Yes, there was a measurable difference. G6Sulfur, the stratospheric aerosol injection one, was found to be slightly more effective than G6Solar, the general dimming one, particularly in reducing TXX, the daytime highs, by maybe an additional 0.5 to 1.0 degrees Celsius in continental regions like northern Vietnam, Laos, Thailand, and Myanmar. This performance difference is likely down to how stratospheric aerosols actually distribute themselves and their specific radiative effects. It shows that, not all SRM approaches are created equal in their impact.
So SRM looks pretty promising for much of the region, cutting down that extreme heat. But did the study find any areas where it struggled, where it was less effective?
It did, and this is a really crucial caveat. The study observed limited effectiveness for SRM in specific maritime subregions, places like Sarawak and Sabah in Malaysia, particularly for those daytime maximum temperatures, TXX.
Interesting. So back to the maritime areas again.
Exactly. It highlights that even a global intervention like SRM isn't a perfect blanket solution. Local climate dynamics, especially complex interactions over water, can create unique resistances or dampen the effect. It means that even with this potentially powerful tool, some very vulnerable communities might still face significant heat stress, underscoring the need for localized adaptation strategies alongside any global measures. These are just complex regions, Unique land-sea interactions, lots of convective activity, strong monsoon influences. It all plays a role.
And speaking of those maritime regions, the study highlighted their heightened sensitivity to heat extremes in general. Why is that? What makes those areas particularly vulnerable to begin with?
Yeah, maritime regions in Southeast Asia show this heightened sensitivity due to a few factors working together. First, there's high atmospheric moisture. More water vapor means a stronger greenhouse effect locally, amplifying warming. That's the water vapor feedback loop. Also, you tend to have relatively stable boundary layer conditions near the surface, and often less difference between day and night temperatures compared to inland areas. This allows the warming signal to kind of manifest more directly. And finally, things like warm pool dynamics in the ocean and vigorous convective processes can further amplify the temperature response, making them particular hotspots for extreme heat.
Okay, so with these numbers and findings in hand, let's just step back for a second. Fundamentally, how is SRM actually achieving this cooling effect? And maybe more importantly, what are the critical red flags? The undeniable disclaimers that come with even considering such a powerful planet-altering tool?
Right. The core mechanism is pretty direct. SRM reflects incoming solar radiation before it can be absorbed by the Earth system. This directly lowers surface and atmospheric temperatures. And by doing that, it directly impacts the thermal conditions that drive heat wave formation and intensity. Simple in concept, complex in reality. However, and the study makes this absolutely crystal clear, this cannot be overstated. SRM is not a substitute for reducing greenhouse gas emissions. Full stop. It's presented only as a potential temporary supplementary measure, something to perhaps reduce immediate climate risks while we get emissions under control.
Yeah.
It might buy us some time, maybe, but it doesn't solve the underlying root problem of too much CO2 and other greenhouse gases in the atmosphere.
Right. It treats the symptom, not the disease. And even with these positive projections just for temperature, SRM still carries significant uncertainties and potential risks, doesn't it? We're talking about unintended consequences, the ripple effects of such a massive intervention.
Precisely. Huge uncertainties remain. SRM carries risks like potential disruptions to regional atmospheric circulation patterns. Think about shifts in monsoon systems, which are absolutely vital for agriculture for billions of people. Alterations in precipitation patterns are another big one. You could potentially see devastating droughts triggered in some tropical regions, while maybe rainfall increases, perhaps damagingly, elsewhere. And beyond the direct climate impacts, there are equally critical socioeconomic implications. Major concerns exist about uneven regional impacts, who benefits, who suffers, issues of fairness, huge governance challenges. Who gets to decide if and when to deploy this technology and how? And what about potential political tension between nations if deployment were to happen, especially if impacts cross borders? It's incredibly complex.
That leads perfectly into policy and future considerations then. Given its power, but also these inherent risks, what does the study suggest about how we should approach any potential SRM deployment?
It calls for an extremely cautious, well-regulated approach. That's the bottom line. This means absolutely comprehensive risk assessments that look far beyond just temperature impacts. We need to evaluate potential effects on precipitation, atmospheric circulation, ecosystems, agriculture, everything, and the socioeconomic consequences. International cooperation is flagged as absolutely critical. We need mechanisms for equitable decision-making, transparent governance, and ways to manage any transboundary effects, because the atmosphere doesn't respect borders, right? The study also emphasizes the importance of investing heavily in monitoring systems, robust public engagement, bringing society into the conversation, and building adaptive capacity in vulnerable regions to minimize any potential societal risks. It's basically a call for extreme diligence and global collaboration before we even think about taking such a step.
So this deep dive has really shown us that these solar radiation modification strategies, particularly the G6Solar and G6Sulfur models they tested, they do show significant potential, at least in the models, to mitigate that dramatic intensification of temperature extremes and heat waves projected for Southeast Asia under the really scary high emission scenarios. They could bring those impacts much closer to what we might see under a more moderate emission pathway.
That's right. That's what the modeling suggests for temperature and heat waves specifically. However, as we've thoroughly explored, this comes with really important caveats. We've seen its potential limitations, particularly in those maritime areas for daytime temperatures, and we've discussed the ever-present and frankly quite worrying potential for unintended consequences beyond just temperature, things like shifts in vital precipitation patterns. The core message from this study and the broader research seems clear. SRM is a potentially powerful tool that might supplement emission reductions, maybe reduce harm in the short term, but it absolutely definitely does not replace them.
This deep dive really shows us a powerful tool, doesn't it? Something capable of significantly altering our planet's temperature. And it forces us, I think, to confront a pretty profound question. If we actually develop the ability to dial down the sun's impact, what are the ethical lines we might be crossing? Or perhaps, what ethical responsibilities are we avoiding by not considering such interventions, especially for regions already suffering, and for places like Southeast Asia, already on the front lines of climate change, desperate for relief? How do we possibly balance this urgent need against the long-term, largely unknown risks of deciding to play architect with our entire atmosphere? It's certainly a conversation that's only just beginning.